We've seen previously how quantum phases can be used to output the results of a quantum algorithm. Now we're going to see a technique for estimating these phases that incorporates another quantum algorithm in order to ensure that we get a precise estimate. Relative phases are important and ubiquitous in quantum information. We can produce one of these relative phases using a unitary U by inserting an eigenstate of U, which we call psi k, into a controlled U operation, resulting in the corresponding phase phi k being kicked back onto the control qubit. Alternately, we can produce a relative phase in a physics experiment. For example, assume that we have a beam splitter here that splits an incoming light beam into two paths, one of which passes through a piece of material that shifts the phase of the light's wave function. This can produce a physical state with that relative phase on it. Now we come to the question, how do we learn the values of these phases? If we input a plus state to the phase gate phi, and then measure in the x basis, the plus state transforms from 0 plus 1 over root 2 to 0 plus e to the I phi 1 over root 2, which has coefficients 1 plus e to the I phi and 1 minus e to the I phi in the plus-minus basis. This results in a probability of measuring the output to be in the plus state that is 1 plus cos theta over 2. Let's take a look at the performance of the cosine of phi measurement. Now, phi is a point on a circle, and the cosine of phi is the x-coordinate of phi, just on the x-axis there. Already we can see one of the problems with doing a cosine of phi measurement on its own. There's another angle phi prime with the same cosine as phi, making it impossible to tell the difference between them with only these measurement results. Now, if that weren't a big enough problem, there's also the fact that if we have some imprecision on our measurement of cos phi, suppose for instance that we know the cosine of phi is in this gray band, but not where exactly, then our estimates of phi get very imprecise when phi is near 0. This is in contrast with the situation when phi is close to pi by 2, or 90 degrees, where the same amount of imprecision on cos phi results in much less imprecision on our estimate of phi, a much smaller blue wedge seen here. So how do we fix this? Well, we can run a second type of experiment, which involves preparation of the plus I state, which is 0 plus I1. Then we feed that through the phase gate and measure out in the x basis as before. If we do the same algebra to analyze this experiment, we end up with a probability of measuring the plus state, which now depends on the sign of phi, which is the y-coordinate of phi in the diagram we drew previously. Now, we have only one range of angles that's consistent with both our imprecise estimates of sine phi and the cosine of phi. Also, note that the precision of the estimate is independent of phi itself and remains the same as we travel around the circle. This precision, the width of the interval for phi, scales as 1 over the square root of s, where s is the number of measurements. Now that's all well and good, but you may wonder whether we can do better. We can, in fact, but first we'll have to consider a simplified case of phase estimation. Let's focus on the phases 0 and pi. In the plus state experiment from earlier, these angles produce a probability of measuring plus that's either 0 or 1 exactly. As long as we're guaranteed that the phase we're trying to estimate is one of these two values, then one measurement suffices to give us exact knowledge of the phase, so we don't need to worry about precision. To generalize to other smaller angles, we'll need some notation, namely that of binary fractions. Here, we express phi as 2 pi times a number omega, which is between 0 and 1. Omega is a sum over these values bk, each of which can be 0 or 1, times 2 to the minus k for k ranging from 1 to infinity. We can write this out as 0.b1, b2, b3, etc. For example, 1 over 2 will now be denoted 0.1, where normally you would use 0.1 to denote 1 over 10 in base 10. Also, 1/8, 1 over 2 to the 3, will be 0.001, and we can express other fractions like 3/8 as binary strings like 0.011. In order to make full use of this notation, we'll also need to note that we can control the phase that gets kicked back by applying multiples of phi rather than phi itself. This is true both in the case where we use phase kickback from a quantum circuit and in the case where we're doing a physics experiment. The main difference between these two cases is that in a quantum computer, u to the mth power may be implemented more cleverly and in less time than simply doing u m times in a row, as you have to do if you're running one of these physics experiments. For this reason, let's assume from now on that we're doing a simulated u in a quantum computer rather than a direct physical u in a physical experiment. Now we're ready to estimate phases that have one of four values, 0, pi by 2, pi, or 3 pi by 2. There are a few convenient facts to discuss. First, we recall that e to the 2 pi I is 1. Next, we use this fact to derive that applying the four-valued phase twice gives us a two-valued phase, which is either 0 or pi, depending only on the value of b2. This gives us an intuitive algorithm to follow to learn phases with these four values. First, we apply the phase 2 phi to the plus state and perform a single measurement to learn the value of b2. Then, we prepare a new special input state that cancels out the phase 0.b2 and perform another measurement to learn b1. As long as we can adjust the phase on the input state such that the output state always has a phase of 0 or pi, one measurement is all we need to determine that bit of the phase exactly. Now, in order to estimate arbitrary phases, we begin by choosing a number of measurements that we'd like to do, and we'll call it s again for simplicity. We apply the phase 2 to the s minus 1 phi to plus to learn the last bit of b that we're interested in, call it bs. Then we adjust the phase on a new input state to get rid of the last bit on the output, and we apply 2 to the s minus 2 phi, so that the output phase is 0.bs minus 1. After this, we can continue canceling known bits of the phase by shifting the input state, and canceling unknown bits of the phase that we're not yet ready to measure by applying a multiple of phi, until we've learned all of the bits of omega that we wanted. Since this returns one of 2 to the s uniformly spaced values around the circle, we get a precision that's 1 over 2 to the s, much more precise than the 1 over root s scaling we saw earlier. And one of the final very special things we can learn about this procedure is that it can be implemented coherently, using all of the phased plus states at once. We take advantage of the fact that, if we perform a Hadamard on a state with a 0 or pi phase, we get a state that's 0 if the phase is 0, and 1 if the phase is pi. Then, we can use these states as the coherent controls to phase shifting gates that perform the shifts we discussed earlier. If we write out the entire circuit, we see that its inverse would take a bit string as input and return a set of phased states where the phases encode those bit values. This is precisely the quantum Fourier transform, which underpins many quantum algorithms.